Hello students, welcome to a lecture on cyber physical systems. I am Samir, research scholar at the Department of Computer Science, CUSAT. This is a continuation of the previous lecture that covered models of computation, including the synchronous reactive model of computation. Today we'll be looking at the Dataflow model of computation and other models of computation, including dynamic data flow, the various variants of the Dataflow model of computation, including synchronous data flow, dynamic data flow, structured data flow. We will also have a look at the timed model of computation, especially with a focus on discrete event systems. Let's move forward. A quick recap, or rather a clear understanding of what exactly is a model of computation. We know that a complex cyber physical system is involved of several actors. Each actor has a specific role implementing or realizing a key functionality of the entire system. If you look at the interactions that occur between the various actors, there are a lot of questions that arise. How do the actors get fired? When each actor fires, how does the various elements that are involved respond? Do actors fire when they have data, or do they fire when there is a particular event that occurs? Now this gives rise to several various other questions, and briefly we can summarize, or rather compartmentalize all these questions into three different aspects. The first being what constitutes a component, which is the fundamental idea behind an actor. The second is how the actors actually communicate simultaneously, which involves concurrency mechanisms, which we deal with almost every time when we talk about actors who respond, or rather who react at the same time. Now finally the question, important question, how do they communicate? So the three set of rules form the model of computation and actually gives rise, or actually gives us an idea about how the system is realizing the complex cyber physical system that it's modeling. Now the Ptolemy tool was actually created with an idea to enable heterogeneous models to be developed and simulated together as part of an overall system model. The key innovation in Ptolemy 2 supports multiple MOCs that are tailored to specific types of modeling problems. The MOCs define how the model will behave and are determined by the director that is used within that model. So here I am just talking about Ptolemy, which is the simulation tool that almost every one of you have actually used during their hands-on experience. Ptolemy is a modeling and simulation tool, and one of the important features of Ptolemy is that unlike other tools, or unlike most of other tools, it supports multiple models of computation, which enables students as well as researchers to try to experiment with different kinds of systems which have different models of computation. And all the semantics, or at least almost all the semantics, of each model of computation is captured by the Ptolemy tool. Now you have seen a particular word that I have used here, which is called director. Now this particular word is clear enough or straightforward when you consider the concept of an actor. So there are several actors that are involved in a complex cyber-physical system, and basically a director has the job of coordinating and ensuring that there is a permanent semantics that is defined in the screenplay, or rather during the execution of the system, when all the actors have to communicate between each other and perform certain actions in order to realize the functionalities of the system. Moving forward, what is a director? A director basically realizes a domain which is an implementation of a model of computation. So what this means is a domain and an MOC along with the director are closely coupled. So for example, in Ptolemy, when you actually construct a model that contains a synchronous DataFlow director, you have constructed a model in the HDF domain using the HDF MOC. So let's see that how that happens. So we have taken a small example in the Ptolemy tool. This is basically a periodogram spectral estimate of a modulated sinusoidal noise. So here what we are trying to achieve is we are inputting a signal source along with a carrier source and a noise. Now all these are actually combined using this particular actor, and we pass this to a spectrum actor. It provides a time frequency domain display. We also have a time domain display. So rather than going into what exactly this example does, we have to look at this particular element, which is an SDF actor. So the SDF actor, if you just try to get a documentation, you can see that an SDF director basically implements the Syncrhonous DataFlow model of computation. So as we start talking about the DataFlow model of computation, we will talk about more about how this example implements DataFlow. So let's go back to our presentation. So let's start by discussing basic things about this DataFlow model of computation. So we have already seen the synchronous reactive systems. The word itself, synchronous, denotes that there is some fixed synchronizing mechanism whereby each actor responds or reacts to certain events. Now we are going to look at asynchronous mechanisms or models of computation, unlike SR. Why we need those kind of models of computation is that we want to have certain implementations where the reactions may occur at the same time. For example, like SR at the tick of a clock, or it may not occur. So in such situations, we have to have a asynchronous model of computation. So how do we justify the DataFlow model of computation is asynchronous? Now for the DataFlow model of computation, the occurrence of a reaction or the simultaneity of the occurrence of a reaction is not part of the semantics. When a reaction occurs, whether a reaction occurs is entirely within a particular actor. So this doesn't mean that there is no coordination at all. We will see how that is achieved, but compared to a synchronous reactive system, this is basically an asynchronous model of computation, and it's decentralized. So as I was telling you, the reactions are dependent on one another. Let's see how. Taking the same example that we just saw, we can see that this actor, particular actor, which if we try to open, we can see is implemented by this Java code, tries to achieve or perform certain action. It implements a certain functionality which basically is calculating or basically is combining the three signals and providing that to a spectrum. Let's just run this application, and this is what we obtain. So rather than going into detail about what this actually does, which is beyond the scope of this lecture right now, is the point that this actually combines the three signals based on data that is received from these three actors. So this particular block is dependent on these three actors, which are the signal source, the carrier source, and the noise source, and it uses this in data to combine. So this brings us to the question of the firing of actors, which we will be discussing right now. So let's just have a quick look at the practical implications of the DataFlow MOC. We know that DataFlow obviously are a requirement for applications that involve processing of streams, data values. So there is a dependency in terms of data between two actors. The streams can flow through sequence of actors, and they transform these streams in some way. Just like in this example, we are actually transforming the signal or a combination of the signals into a spectrum which is being displayed. So this transformation is carried out by this actor here. The models are often called pipe and filter models. So what does this pipe and filter mean? So basically it means that the data that actually flows through the various actors, which is basically the connection between this actor, can be considered as a pipe. So this is basically a kind of a pipe, and this pipe actually takes data, or it actually moves data from this actor to this actor. This is a pipe. And what does a filter mean? Okay, so what does this filter mean? It means that there is a, at each stage we have certain manipulations of these data flows which are done by certain actors. So the pipe stands for the connections, while the filter stands for the actors that actually perform changes on this, perform some actions on the data flows to make changes to the data flows. So the important aspect that we want to talk about here is the DataFlow models or DataFlow domains basically ignore time. So when you look at this, it says that it ignores, or it rather mostly ignores the time. So what this means is the DataFlow models basically don't have a notion of the time in terms of synchronization, but they have an idea of time, or they have a notion of time in general. So if you look at the second statement, which we can see that there is a synchronous data flow. So basically what we are talking about is asynchronous models of computation, but here the word synchronous data flow may be creating confusion for you, but we will look at this in detail after this slide. But here the synchronous is actually a confusing term, but I will talk about that in detail. So synchronous data flow definitely has a notion of time because it models streams with uniformly spaced time between iterations. So this is what I was just talking about, the data dependence. The reaction A requires data produced by reaction B. Here this actor requires data that is produced by all the three sources in order for it to fire. Now I define a Dataflow model of computation is a model of computation where such data dependencies are the key constraints on the reactions. So for each actor to react, there exists certain data dependencies, and if a data dependency is resolved, each actor fires and performs the necessary action. So this is the another example that we can see. It's basically a similar example that we have seen, but it involves some more actors. So you can look at the annotation which says that this is an example that is well suited for signal processing. Since this lecture is not the signal processing concepts are quite out of the scope of this lecture, we are not going into detail about this example, but here we just want to emphasize the aspect that the components communicate using streams, which is the stream. So this actor, which is a sine wave actor, actually produces a sine wave, and these are the other actors which are the same actor, but they produce three different sine waves. So the three different sine waves are combined using this add subtract actor, and the input is given to the addition input port, which means that the actor actually adds all these sine waves and produces the spectrum, the smooth periodogram, and the maximum entropy spectrum. So these are the three actors that we use, which basically they are spectrum actors. And finally we give this to a sequence plotter. And we also have an addition here. We're actually giving a Gaussian. So basically this is a noise that we give here, and we have a filter also here. So moving forward, let's talk about some basically formalized definition of data flow. So in data flow, we have a sequence of tokens that actually they provide the communication between the actors. How do they provide the communication between the actors? So what exactly is a token? Okay. This is the question. So basically a token carries some data, and it is this data which is basically encapsulated in a token, and token is received on the input port, and a token is produced on the output port. So basically each time they fire, or each time an actor fires, he consumes a token or produces a token. Now let's talk about a signal. Okay, so what is a signal? Okay, so basically a signal is the signals provide communication between the actors, okay, and they are basically sequences of tokens, and this signal S, okay, is a sequence of token, and it can be represented in as a partial function, okay, which maps from the set of natural numbers to Vs, which is Vs is a type of signal. So so what is Vs? It's a type of the signal. So you can map from the natural numbers to a signal type. Now what this means is that basically the signal is defined on a set of natural numbers for finite executions, and when we talk about partial function, it means that the signal, it doesn't exist all the time. So basically it doesn't exist at each single instance of time, or if we have a clock, maybe a global clock for example, for reference, it need not be present at all times of the global clock. So why does this happen? So basically unlike the synchronous reactive systems that we have seen, this is an asynchronous system, in terms that in a sense that this actors only fire when there is data that is available, so there is a data dependency. So actors only fire when there is a data available, basically if they have a token that they want to consume, else these actors don't fire. So this is a partial function, and it only doesn't exist for all the periods in this particular set of natural numbers, or for finite execution it doesn't exist, or it doesn't execute or fire at all instances of this finite execution. Now each element S of n is basically a token, Now, a determined actor is basically a function. It maps the input sequences to the output sequences. So we know what is a sequence. A sequence is basically a sequence of tokens. Basically, it models a data flow. Let's directly jump to an example. So in order to look at an example, let's talk about the scale actor that we have seen in the previous chapters. So basically, a scale actor takes as input a certain value, and it has a parameter which is the scale or a constant value, which actually multiplies with the input to produce a y1. So this is an actor that is mentioned here. Now let's assume that the input type is from the real domain, and the scale actor is parameterized by a parameter which is also from the real domain, and it multiplies this the real value with a constant real value. Now let's come to directly to the example. So we have a parameter a, and this is as I was talking about the pipe and filter example. Here the pipe is the connection that comes as input, and this is the filter, which is basically the scale actor, and this is another pipe which produces the output. So here we have a function which takes as input x1, x2, x3 and produces ax1, ax2, x3. So basically here as we receive tokens, and each token or each data item or each input value is multiplied or scaled by certain constant value. Here it is a, and it's multiplied by a, and it performs one multiplication when the actor fires. Okay, and then if I act the firing function, basically this job is only to multiply each input by a constant value. And so if you talk about the firing function, let's say that the firing function operates, if you say the firing function operates on the only a particular value, we use small f to denote this particular value, which is f of x1, and it gives an output a of x1. So here the output sequence is only of length 1. So when we talk about the a continuous or infinite firing, we use the capital variant of the letter f, and it produces an output which is a continuous stream of output, each multiplied by a constant value. So the actor is represented here as f, which is the firing function, and f is the firing function for a finite sequence, which basically multiple invocations of the firing function f. So the capital F is a multiple invocations of the small firing f, and a small firing f, firing function f is just produces an output sequence of length 1. Okay, so this is what I just mentioned. So this is small f denotes a finite sequence or a finite portion of the input sequence to the output sequence. So a capital F and a small f denote the firing function. Now, so what is a firing rule? Now a firing function can be invoked, but can be invoked with only partial information about the input sequence to the actor. A firing function can be invoked with only partial information about the input sequence to the actor. So what does that mean? Okay. A firing function can be invoked if one or more tokens are available on the input. So this is another thing that we can say. So the question is, what about the SR actor? Okay, there is another question that we want to ask here. What about a synchronous reactive system? So what do you think in the case of synchronous reactive system? So for a firing rule, basically we require only one input. Okay, so we require with partial. So if you have a particular data that is available, the actor immediately fires. So for example, the example that we just saw of the signal processing example that we just saw, in the signal processing example, as the values of the signal are received, or partial information about the signal is received, actually operates and produces the output based on the input tokens that are available. So as we can see, it consumes one input token and produces an output token. Okay. So a firing function can work with only partial information. In the case of a synchronous reactive system, the story is different, because a synchronous reactive system will fire, or it only fires when it has sufficient information to produce the entire output. So basically it works in a different fashion. So here we are actually talking about the different ways in which a cyber-physical system works. So in the example that I just told, the scale actor actually uses a firing rule, and it requires only one token. So the question is, can we have a requirement for more than one token? Definitely yes, we can have a requirement. So if a particular actor is designed in such a manner that it says that I need these many number of tokens to fire, of course that can be satisfied. But in case of a scale actor, it only requires one token. So it's quite simple, and we say that the scale actor can work, or it can fire when it receives only one token. So this is the different ways in which our systems can be designed to work, and models of computation will provide the semantics for how our system should work in such a fashion. Now let's define a firing rule formally. A firing rule basically specifies the number of tokens required on each input port in order to fire the actor. It's simple as that. It just tells us how many tokens that we require on each input port in order to fire the actor. So this is clearly defined in the semantics and can be clearly mentioned in the actor. Okay, so we will just take a look at a quick look at an example, and then we will move to synchronous data flow. We will talk about a few more things in general, and then we will move to synchronous data flow. So let's look at this example. In this example, we are talking about an actor which is called a delay actor. So what is a delay actor? So delay actor basically it has parameter d, and if the actor actually prepends a sequence with a token value d, and it has two firing functions and two firing rules. So we have two firing function, which is the d1 and d2, and has two firing rules. So what are the two firing rules that it has? Okay, so the first rule. So first rule is when there are no input tokens at all. So when the system starts, okay, and we know that there is an actor. Okay, if you have one actor that is connected to this delay actor, okay, so let's say that this actor, which I will denote as A, and it actually produces an output, and this output is actually given to the delay actor. Okay, so the delay actor I will denote by D. So what will actually happen is the actor A initially, when it fires, it doesn't produce any output. So there is no output at the input port of the delay actor. So the first firing rule says that if it doesn't have any input tokens, okay, at all, okay, it doesn't it requires no input tokens, and it just produces an input sequence of length 1, output sequence of length 1. So basically if it doesn't have any input token, it just produces an output token of length 1, which is the D that you see here. So here the initial value that will be produced is D. Now what happens? Okay, now this is the sequence. So it can be the first firing rule it requires is basically can be represented like this. So the output will be the first firing rule D1. If you give a sequence as input, it just produces D. So basically in the first firing rule there is no, it's a null sequence, or the basically it can be a sequence of length, it can be sequence of length, any length, it can be a sequence of length 0. Basically it's an empty sequence. So if it's a sequence of length 0, it produces an output D. Okay, so this firing rule is initially the one used, and it's only used exactly once. Okay, so what about the second firing rule? Okay, so here we have two firing rules, the first firing rule and the second firing rule. What about the second firing rule? In the second firing rule, the actor actually produces the output from this actor. Will be there will be an output from this actor, and it will receive a token on here. So there is an input, so sequence of length greater than 0. Okay, so length at least minimum 1. So the output that will be produced is basically is just copies the output. Okay, it just consumes one input token and produces output same token. Okay, so now we will have a look at the finite state machine. So before that, we just need to get an idea about the concept of the firing rules. So here there are actually two different firing rules. So why we have two different firing rules? Basically, there are two rules. One rule is when there are no input tokens available, and the other rule is when there is one input token available. So if there are no input tokens available, the output is just D, which is what is prepended here. And when there is an input token which is of length 1, for example, if the input token is of length x1, in the next firing it will produce an output of length 1, which is x1. Similarly, when it receives x2, it produces an input of length x2. So whenever the input is 0 or there is a input of, it's an empty sequence, it basically produces a value D. So this is the purpose of a delay actor. It just prepends a delay token at the beginning of the input sequence of an actor. So you can say that it just pushes the input an extra step. So what is the purpose or what is the function of a delay actor? It's just to introduce a delay. So what is the point of introducing a delay? So we will see exactly point in synchronous data flow how we can implement this, or how we are going to use the delay actor. Now coming to the state machine. So here we see that if the input is so if it receives an input, it will be in state S1. Once it receives input, so the initial state will be S1, and only when it receives real input, it will be producing an output basically. Okay, so here after moving to the initial state, it will whatever input it receives, it will move to state S2. Okay, so please note that the initial state, once it moves to the initial state, at the first firing, it will use the first firing rule D1, and it will just move to state S2. It will not. It will only produce the output D, which is the output that is given here. The guard condition is true, means that whatever be the input, it just produces an output D. Okay, and in the next firing, it will actually produce the previous input, which is X. Okay, so this is the input that it received in the previous firing, and that it will be producing the input X. So basically, it will just add it will just produce an initial value D, and then it will continue to produce the data that it receives on its input port. So let's move forward. Yeah, so two more things that we need to talk about are the aspects of buffering and deadlock. So let's just talk about buffering, which is an important aspect. So obviously, when we talk about data flow or data streams, there arises a question of where this data stream is stored, or in where is the intermediate storage, or is there a caching or buffering kind of system. So we know that the data flow actors are composed basically the input of one actor. For example, the actor here is A. The output of A is going in input of B. The communication is quite different from previous model of computation that we have seen, especially synchronous reactive, because the firing is asynchronous and the actor is only fired when the firing rule is activated. So when the firing rule is activated, the actor needs to buffer its data so that it doesn't lose it. So in the previous case of the delay actor, we know that the data that it receives, for example, the value x1 that it received in the previous iteration or the previous firing, it stored this value x1 into a buffer, and it produced this value x1 in the next firing. So similarly, we need to have a buffering mechanism here where the data needs to be saved until a particular firing rule is activated and the destination actor is ready to consume it. So this buffering will happen at a particular place, and this buffering has to be done basically by the it has to be taken care of by the director. So this buffering is done by the actors themselves, and it has to be coordinated by the director, which is the SDF or the synchronous data flow director. So let's take an example. Let's quickly look at an example. When the destination actor fires, okay, it consumes one or more input tokens. After being consumed, a token may be discarded. the buffer memory may be reused. So if you consider the example of this example which I just showed you, it's a cascade composition of data flow actors. Now A doesn't have any input ports, so its firing rule is simple. It just can fire anytime, so it doesn't have a data dependency. So if A had a data dependency, we would have to have one more firing rule which says that when the data arrives at A, it has to produce an output at B, for example. So since A doesn't have an input port, doesn't have a data dependency with any other actor, it just fires at any time according to its convenience, or rather according to its pattern of execution. And let's suppose it produces one token. And on firing, and the B also consumes one token. So S is the signal. Basically, it's a sequence of tokens, and B consumes exactly one token, maybe. So if A produces one token and B consumes one token, then this is fine. This is a perfectly stable composition. But what if A produces two tokens and B just consumes one token? So what happens to the other token? Where is it buffered, or is it lost? So this is one problem. Okay. So this is one problem. Basically, we are talking about actors that produce tokens, and we need to understand like where this tokens are stored, and we may have a long if these tokens are indeed buffered, what would be the size of the buffer? So each time A fires, B consumes one token. Say if A produces 3 tokens and B just consumes one token, we will have a build-up of a large number of tokens. So we will be requiring a huge buffer. So is this practical? So this will lead us to something which is called unbounded execution, and we will have a requirement for a huge storage. So basically this becomes impractical. So the system needs to have a suitable mechanism of semantics, so that we should prevent this unbounded buildup of unconsumed tokens on the buffer between A and B, rather than exhausting all the available memory. So here we have a restriction that we have put in place, which is basically a requirement that when A produces M tokens and B produces N tokens, we need to have a mechanism where the values of M and N should match in such a manner, or the values of M and N should be in such a manner that it leads to a bounded execution. So basically our requirement is for a bounded buffer, and also to prevent deadlock. So when does a deadlock happen? So basically B requires maybe N number of tokens for firing, and A produces M number of tokens. Well, let's say that the value of M is basically equal to 1, and the value of N is basically equal to 5. So this becomes an issue, because A has to fire 5 times so that B can get 5 tokens so that it can fire. So this becomes a problem when it's actually deadlocked, and also there can be a situation when there is a feedback loop. So let's suppose that there is a feedback loop here, and the feedback loop, what happens is that since A has to get input from B, B has to produce some tokens in this feedback loop, so that A can receive its input and fire. So until B produces something, A cannot fire, and only when A fires, B can fire. So this becomes a deadlock. So what we usually do is that we actually put a delay actor in this feedback loop, and or we add some tokens in this feedback loop, extra tokens, so that A can start firing and to prevent the deadlock. So we will see these things in detail when we talk about the synchronous data flow. We will give clear methods for detecting deadlocks and actually preventing deadlocks, and giving solutions for unbounded execution, to prevent unbounded execution. So this is about the bounded buffers and the deadlock. So it's very difficult in Dataflow models to tell when the system will deadlock. So basically there is no algorithm, or it's basically an undecidable problem or question when we say that a system in order to detect whether the system is deadlocks or not. So there have been several works and some promising works have been done, and there are some algorithms that have been designed that actually gives us the able to answer this question in bounded time for all the Dataflow models. So let's move forward, and this is what I was talking about. So again, here we have a deadlock due to this feedback loop from B to A, and then when there are cycles, it will result in deadlock. So how can we prevent deadlocks is the question. So we can add a delay actor, and we can produce an initial input token. So when there are no input tokens, so basically this will be a problem. Okay, so in every cycle we need to have a delay actor. Okay, so let's move into synchronous data flow. So let's continue our discussion on synchronous data flow. So basically it's a constrained form of data flow. So what this means when I say constrained form will be more clear as we move forward. So the basic idea remains the same. Every firing consumes a fixed number of input tokens on each input port and produces a fixed number of output tokens on each output port. So what does this mean? This is a determinate actor. So we have already seen what determinate actor is. It doesn't produce excess or unnecessary tokens, extra tokens on firing. It only produces those tokens that it has received on its input ports. Okay. So this is one diagram that we have seen earlier, and I had mentioned to you that the output from the actor A produces m number of tokens and on firing, and B requires n number of tokens for B to fire. Let's say that A fires QA times and B fires QB times. So since A fires QA times and B fires QB times, we need to have an equation that also takes into consideration the values m and n. And of course we know that if you have an equation, and for balancing the equation on both sides, we need to have a multiply, make sure the quantities are the same. So the variables here are QA and QB. So we need to find out a schedule that delivers unbounded execution with bounded buffers. So we must note the two highlighted terms. The unbounded execution means that we need to have an execution that ensures that the execution is unbounded, okay, and it doesn't stop due to lack of tokens, but it should have we should be able to manage this execution with bounded buffers. Let's consider an example so that we want to balance the two equations, two sides, QAM and QBN. M equal to 2 and n equal to 3. So what are the values of QA and QB that satisfies this equation? What will be the schedule? So let's try to work this out. So this is quite straightforward. So let's say that if m equal to 2 and n equal to 3, we can have a value of 3 for QA and 2 for QB to satisfy this equation. Yes. So that means that we can have a equation that balances with 6 on both sides, and we have QA and QB. So what is this QA and QB? QA is the number of times that A fires, and QB is the number of times that B fires. So if you have a schedule that can be repeated, so please note that we are talking about a synchronous data flow actor. Okay. Now in a data flow actor, basically we have a requirement, a data dependency between the two actors, in the sense that when one of the actors actually produces the data, one of the actors actually produces the data on its output port, another actor that is actually has a connection with this actor needs to consume the data and produce a token. So we have a schedule. That means we need to have a asynchronous firing for these both actors, so that it leads us to unbounded execution with bounded buffers. So this is what we want to we want to prevent we want to prevent a situation where the actors don't fire due to lack of tokens. So this is one of the schedules that we can implement. Actor A fires first, actor A fires second, and actor A fires third. So in this case, the SDF director actually enacts, or basically it fires the actor A 3 times. So since we have determined the value for QA is equal to 3, and this leads us to a condition where we have actor A firing 3 times, and because of actor A firing 3 times, we have 3 tokens. Basically, we have 6 tokens that are available. Now, when the 6 tokens are available, the actor B is ready to fire. So remember, the actor B fires 2 times, consumes 3 tokens on each firing, while actor A produces 2 tokens on each firing. So this balances the equation, and now B has sufficient tokens for it to fire. Now we can have an alternate schedule also. What is an alternative schedule? We can have actor A fire twice, which produces 4 tokens. Of course, B just requires 3 tokens to fire. So we have A firing twice, and then B firing once, and A firing once, and then B firing once. So this is a alternative schedule where we have 2 times A firing, producing 4 tokens, which is sufficient for B to fire, and then A fires again, which produces 2 more tokens, and there is 1 token remaining from the first 2 firings, which has 3 tokens, and then B fires again. So what is the advantage of this is the question. What is the advantage of this schedule over this schedule? What is the advantage is the question. So this is quite straightforward. Maybe you can just give a thought and see what is the advantage. Well, the advantage is that the second schedule it requires less memory, because you have only 4 tokens at a time that needs to be stored, so the size of the buffer is less. But in the previous schedule, you actually have 6 tokens that you need to store, and there are 6 tokens that you need to store in comparison to the 4 tokens that need to store in the latter schedule. So this 4 tokens actually help us reduce the memory requirement, and hence this schedule is more preferred in terms of memory usage. Now we can have all other solutions, but they are infeasible. For example, you can have a solution where QA is equal to 6, QB is equal to 4. So if you just try to multiply this, this says that it gives you 12 on both sides, in QA into M and QB into N. But what is the if this is a solution, okay, so this is a solution, okay, this is a feasible solution, okay, but this is infeasible due to the reason that the number of firings that you require for A is quite high, okay, because A, you can see that the alternative schedule that we have given here, which is number 2 or B, the alternative schedule is an optimal schedule in the sense that we can have the bare minimum number of tokens that are required by B just with 2 firings of A. But in the case when we have 6 firings of A, we produce 6 into 3, 6 into 2, which is 12 tokens. But B doesn't have to wait for 12 tokens. B can just start firing when it gets 3 tokens. So basically, this is a solution. It's not feasible in the sense because it requires an extra number of firings, which doesn't do any good for the actor B. It has more firings. We can have also a solution QA equal to 0 and QB equal to 0, but it doesn't make sense because actors don't fire. If actors don't fire, nothing happens in the system. Negative solutions are also not feasible. So our objective is to find the least positive integer solution to the balance equation. So for this equation here, we need to find a solution such that we have to find the least positive integer solution for this equation given values of m and n. So hope that is clear to you. So let's move forward to an example that we will try to work out here. So in the previous example we have just seen two actors, but in this example we can see that there are several other there is one more actor, or rather there are three actors, but there are several connections between these three actors. Here we see that there are three connections, AB, BC and AC. Now each connection is basically having a data dependency, and each connection is governed by a balance equation. So we have a system of equations. So let's see how the system of equations look like. So we have three equations here. Let's say QA is the number of times that A fires, QB is the number of times that B fires, and QC is the number of times that C fires. So what is the equation that we have here? Given the values of M, which is 1 here, and the values of N, which is 1 here, we can have an equation which is QA equal to QB. Okay, so let's look at the connection between B and C. So here we see that the value of M here is 2 and the value of N is 1. So we have this equation which says 2QB equal to QC. Now coming to the third equation, it says M has a value 2. Okay, I'm sorry. Okay. M has a value 2 and N has a value 1. So here we have the equation 2QA equal to QC. Now how do you find a solution for this? So just like you solve a system of linear equations, okay, of having three unknowns, we can find a solution for this. Okay, so let's say that the solution that we can find, one of the solutions is QA equal to QB equal to 1 and QC equal to 2. So QA equal to 1, QB equal to 1 and QC equal to 2. So this is one of the feasible solutions. QA equal to 1, QB equal to 1 and QC equal to 2. Can you tell me what will be the schedule for this? What can be the schedule? So when I say QA equal to 1 and QB equal to 1, it means that A and B fire once. So remember, this is the least positive integer solution. So here A fires once, B fires once, and then you have C firing twice. So let me write this schedule here so that maybe you can try to understand how it looks like. A, comma, B, here A fires. When A fires, it actually produces three tokens, okay, on this input port. So let's say this is the input port P, and this is the input port Q. This is the output port P and output port Q. On the output port P, it produces one token, and the output port Q, it produces two tokens. So on the output port P, the one token that it has produced sufficient for B to fire. So this means that we have B firing immediately. Okay. So what about the two outputs, two tokens that it produces on the output port Q? Now the output port Q is connected to the input port of C, which I will denote by T. So the input port of C, which is T, requires one token for firing. So we have two tokens that is produced by A is sufficient for C to fire. So this means that C can fire twice since it has sufficient tokens. So I fire A once, then I fire B once, and then C. So there's one more connection here between B and C. So we know that in order for B to produce two tokens, it has to get two tokens from A, right? So but there is only one token that it receives from A, but for C to fire, it requires two tokens. Okay, so here we can have a situation where we have that the number of tokens that is produced on the output port will be 2. So it requires one token for firing. So B fires immediately. It can produce 2 tokens on its output port, but it only produces one since it fires once. So it produces one token. Now as it produces only one token since it has only one token in its input port, and C has got the token from A, output port of A, that is Q, and the output port of B, which is say small m. So it has output port of B and output port of A. It has received each token from those two ports or those two actors, so it can fire. So it has fired once. Now we see that C can fire once more. So how does C fire once again is another question. So we see that B actually produces 2 tokens. So since B produces 2 tokens, it can actually fire once more. So C has 2 tokens from A and has 2 tokens from B. So it has an extra token, so it can fire once more. So we see that the actor B actually it takes this input 1 token and produces 2 tokens as output. So this is basically a determinate actor in the sense that B takes a fixed number of tokens and produces a fixed number of tokens. It doesn't change this. It can't read 2 tokens and produce 1 token, or it can't read 1 token and produce 1. No, it always takes as input 1 token. That is the minimum sufficient required for it to fire, and it produces 2 tokens on its output. So when it produces 2 tokens on its output, it has an extra token for C. So C takes as input 1 token. Now next time C fires, it takes 1 more token. So the 2 tokens are buffered here. Similarly for A, the 2 tokens are buffered here. So C can fire twice basically. That's what the point is. So this is a suitable schedule, and we can get we can execute this schedule to get an unbounded execution with bounded buffers. So let's move to the second example here. Now can you tell me like what is the difference? So difference here is basically the output tokens of B have been changed from 2 to 1. So let's see what happens in this system, in this connection of actors. So here A produces 1 token, B takes 1 token out as input, produces 1 token as output, and gives it to C. Again A produces 2 tokens, C takes as input 1 token. So here C requires 2 tokens, 1 token on either of its input port to fire. So here we can say that once A fires, okay, then maybe B can fire, and then C can fire. Now what happens after that? Okay, what happens after that. So we can see that once A has fired and B has fired, C definitely can fire because it has got one token on its input port. But what happens next? Now again A has to fire, okay, and B has to fire. So but what happens to the extra the token that A has produced? A has produced two tokens initially, so there is one token there. So A produces one token, and the next time it fires again it produces an extra token. So there is a buildup of tokens at A. Okay, so there is no unbounded execution with bounded buffer. So the buffer size keeps on increasing because the number of tokens at A keeps on increasing and increasing. So the tokens that are, so there is this, basically this system of equations cannot be balanced. It can only be, there is only one trivial solution, which is a non-feasible solution, which is QA QB equal to 0, QC equal to 0. So it cannot be kept in balance because of this reason. So what happens if you put 1 here? Of course, if you put 1 here, this can be balanced because again you can fire A, B, C, again A, B, C. So this can go on forever. But when you have 2 tokens here, it is not possible to keep this system in balance. So hope you have understood the idea of balancing this synchronous and synchronous system. Okay, so now the one point that I want to mention here regarding the word synchronous data flow, basically it can cause confusion because I am talking about an asynchronous system, but I am using the word synchronous here. Now it is not synchronous as in a synchronous reactive system. There is no global clock for a synchronous data flow model. Actors are fired asynchronously. Okay, so some authors use the term static data flow, but that again leads to confusion because there is some other kind of data flow graphs where we use the word static data flow. So we just use the term synchronous data flow, and basically the synchronous word has come from signal processing concept. So here the idea is basically that all the actors are static, or all the actors work in a predefined manner. They don't have any kind of dynamic behavior. So basically this means that the actors are static. So it should have been called a static data flow, but it's called synchronous in the sense because static data flow will lead to a confusion. So the author has used the term synchronous data flow. So there is no global clock. It's not like synchronous reactive system. This is one clarification that I wanted to make earlier regarding synchronous data flow, but I just missed that. So I will move on. Now we will talk about consistent and inconsistent systems. Sorry. So a consistent system is one that has a non-zero solution to the balance equation, and if the only solution is 0, it's an inconsistent system. An inconsistent model has no bounded execution with bounded buffers. So this is what the crux of what we have been discussing so far. Now, if you have to create a scheduler for SDF models, basically the SDF director that we have, the balance equations should have a non-zero solution, and they should have a solution. So the scheduler that they have the work that has been done by the people that have been mentioned here, Professor Lee and Mr. Smith in 1997. They have actually a solution where we have a positive integer qi. So whatever we have talked about finding a balance equation or balancing the equation in order to find an unbounded execution with bounded buffers for a scheduler for SDO models. When we are going to implement this in software, the work that has been done by these people in 1987, they have proposed a solution where they can find a positive integer qi for all the actors. So this is how it is actually implemented. For connected models, they gave the procedure for finding the least positive integer solution as well. So these are the two contributions that have been actually done for this finding a solution to the balance equations. Now, let's talk about consistency. Now, the point that I want to drive here is consistency is not sufficient for an unbounded execution. Okay, so there can be deadlocks. So this is the second problem that we are going to deal, and then we will move into dynamic data flow. So talking about deadlocks. So what exactly is a deadlock? So a deadlock bounds execution when actors are basically stuck Okay, so the actors are stuck because they don't have sufficient tokens on the input port so that they can fire. So remember that an actor needs to have a sufficient tokens on the input port so that it can fire and produce a fixed number of tokens on the output port. So if there is a loop, if you consider this diagram A, it's slightly small, hope you can see it. From the output port P4 of B, there is a feedback loop to the input port P1 of A. If A wants to fire, it needs to have a input on the input port of P1, which can only be obtained if B fires. Now, how can B fire? B can only fire if it has got an input, if it has got a token on its input port P2, which has to come from the output port P5 of A. Now, remember that if A fires, A produces tokens, which B consumes, and B fires, and B produces tokens which A consumes, which can only be used by A for it to fire. So here there is a deadlock. So this is basically a chicken and egg kind of a problem. So who fires first is the problem. So we can actually produce a feedback system like this, like in a cascade composition manner. So when there is a feedback, deadlock bounds execution. So how do we solve this? So we have two different methods that we can use. So one method is where we add a delay actor. So we have already seen a delay actor. A delay actor is one that actually produces a delay. It adds an extra token, and this extra token that is added is actually going to produce it's going to shift the input. So in the initial firing, what happens is that whatever token is produced by A is actually stored, or whatever token is produced by B is actually going to be stored in a delay. The delay actor is going to push it once. The delay actor, it will produce a token, and that token is going to be consumed by A, and so that B can fire. So this is one way that we can handle this problem. So we can also avoid a delay actor. It is not really required. We can have an alternative option with a connection of initial tokens. So this is the example of an initial token. So there may be some tokens that may be available on the feedback loop. So A can basically fire immediately, since it doesn't need to wait for B to fire. So the initial tokens will give a chance for A to fire, and once A fires, B can fire, and then it can go on. So there are 4 initial tokens here. So the question that you may be thinking about right now is, why do we need 4 tokens actually? So let's take an example. Let's go into detail in this example. Let's see that A has a requirement on the input port for 3 tokens. Basically, it produces 3 output tokens. So A requires 3 tokens to fire. So let's say that so the number of tokens that we basically require here is just 3. So why do we require the 4 tokens? Let's see how it happens. So A consumes 3 tokens initially, and it produces 3 tokens on its output, and B consumes 2 tokens and produces 2 tokens. So now we have 3 tokens on A. We have consumed 3 tokens, so let's just cross these 3 tokens out. Okay, now we have 1 token that's remaining. Now B produces 2 more tokens. So I'm just going to add 2 more tokens here. So now we have 1, 2 and 3 tokens. So again A can fire. Okay, so this is the second time, and this causes A to fire, and A produces 3 tokens, and B consumes 2 tokens, and again B produces 3 tokens. So I'm just going to cross this out. Now B is going to produce 2 tokens. Okay, so we see that B takes as input only 2 tokens, so there is an extra token that's available here. So B can fire the second time also, because it has 2 extra tokens. Now this system has been balanced, and it can go ahead without a deadlock, with unbounded execution, with bounded buffer. So this is the solution to this problem with initial tokens. So hope you got an idea about the initial tokens. Probably you can also work it out, and this is the balance equation: 3QA equal to 2QB, 2QB equal to 3QA. This is the balance equation for both the actors, and we can have a solution with QA equal to 2 and QB equal to 3, and this is the schedule that we can repeat. A can fire once, then B. A can fire once more, then B. Again B can fire once more, because it has 2 extra tokens on its input port, so it can fire once more. So remember that each time B fires, it produces 2 tokens. So we need to have minimum of 4 tokens here, so that the system can go in an unbounded execution manner. There needs to be 4 tokens in this feedback loop. If there are fewer tokens, it will deadlock. You can just work this out. It's very easy and straightforward. Okay, so let's look at an example now in Ptolemy. So if you can just give me a second, I will just open this. Before moving into example 3.6 in the Ptolemy, I just wanted to talk about this example that that was supposed to be mentioned earlier. So let's just have a quick look at this example before we move to example 3.6 in Ptolemy. So here we have a sine wave that is produced by the actor, sine wave actor, and it is the sine wave actor actually sends a sine wave through a channel actor to the spectrum actor. So just a quick look at this SDF example. We have an SDF director. Now this is a multi-rate SDF model. So what do you mean by a multi-rate SDF model? So multi-rate SDF model is something that we've seen earlier where different actors fire at different rates. If you look at this example here, the spectrum actor requires 256 tokens to fire. So one iteration of this model requires 256 firing of sine wave, channel and sequence plotter, and one firing of spectrum. So let's just imagine that the sine wave has to say fire 256 times, the channel has to fire 256 times, and then the spectrum actor will fire once. Of course, the sequence plotter will also fire 256 times. So these actors, the spectrum actor will be the one that will be actually being fired 256 times. So let's look at some details of this actor. If you just open the configuration parameter for the spectrum actor, as I have just shown, we can see that this is of order 8. So basically what this means is that it fires 2 raised to 8 times, which is 256 times. So this is of order 8, or the order 8 means it's of power 8. So each time it fires, it produces 256 tokens. So if you just modify this, you can change this value to some other value, and then probably you have to configure the other actors also. Okay. So here we can see that this is the parameter for the sine wave, which basically tells you like what is the sampling frequency. So the sampling frequency for this is basically 8000. So when we say it's 8000, it means that it produces 8000 samples. Okay, and the frequency is 440 hertz. So this basically it produces 8000 samples. Okay, and for this particular sine wave. So, okay, so let's open the channel actor. Okay, it just has a parameter which is noise power. Okay, and the spectrum actor, yeah, I just showed you the spectrum actor, and finally the sequence plotter. So you can see that there is nothing specific here that tells you like how many times the actors should fire, because these actors all fire once. The sine wave actor actually, when it fires once, it's supposed to produce one output token. So basically it samples the signal 8000 times, okay, in a second, and it produces 8000 samples in one firing. The channel actor also fires once. Similarly, the sequence plotter, the spectrum actor fires 256 times, which is configured by the parameter here. So let's run this, and you can see that this is the sequence plotter that you see here. Now if I just try to modify this parameter, rather than say I'll just make it 6. Let's see how it can work. I'll just rerun this. Okay, so you get a different because the number of times it fires is less. It fires only 32 times, so the sequence plotter produces a. So basically what this does is it's just taking a sine wave and passing it through a channel which is a noisy channel. The noise power is quite less. You can also increase the noise power to 0.2, and if you just run this, you get a different plot. So what if you have the noise is 0? So if you just put a 0 noise, it doesn't have any noise, and you can just get the signal, basically the spectrum for the sine wave. Okay, so this is an example that I wanted to talk to you earlier. Now let's go back to our example 3.6 in Ptolemy. So if you let me just open that example. Okay. So this is the example that I wanted to talk to you about. So in this example, we have a few actors here. So basically this is a homogeneous SDF model. So what do you mean by a homogeneous SDF model is so homogeneous SDF model is basically when you have actors, and when there is an input, when there is a token on each input port of a particular actor, it fires and it produces one token on each of its output port. So the director in this case of a homogeneous SDF model has to ensure that each actor fires after. So in the example that we are going to see here, we have an actor which is called the const actor. So basically what does a const actor do? It just produces a constant value. So if you just look at the parameters, it's just producing the constant value, and it sends this value to add subtract actor, and we have a sample delay actor. So this is the actor that we were talking about earlier. So the sample delay actor actually produces a delay, and then this feedback loop that we see here, actually this feedback loop supplies the value from this. So there is a shift basically, and since we know that there is a actually it has two input ports, but we use this input port which is used for the addition operation, and the value that we receive here is basically from the const, and the value that we receive from the sample delay. Now let's see how this works. If you just run this actor, you can see that it's producing values called 0, 1, 2, 3, 4, 5, 6, 7, 8. So each time it adds the value to the previous value that it receives. So initially the value that it receives is 0, because when this actor fires, there is no input from here, and we get a value 0. So the next iteration, the value that we obtain is 1, and then it keeps on getting incremented by each of by adding the previous value, and this is what. So there is one sample delay actor that we have here. So if you just delete this sample delay actor, and without the sample delay actor, if you try to run this, let's see what happens. So we have a message which says that actors cannot be scheduled. So the SDF graph with feedback loop should have an actor with a delay in the loop, such as the sample delay. So this is quite makes sense to see that we need to have a delay actor. So let's just put the delay actor back here, and if you run this, you get the same output. So this is an example of SDF director that I wanted to show you. Now this is what I was just explaining to you, and it just copies the sample delay actor, copies the input to its output unchanged. So this is basically what happens. Okay, so you have seen this already, and now we are actually moving to the next type of data flow model, which is called a dynamic data flow model. So before starting with dynamic data flow, we want to understand like what are the shortcomings of the synchronous data flow model. Synchronous data flow is not very expressive. Expressive in the sense the actors are basically static. They only perform what has been predefined. They do not have any dynamic behavior. especially with regard to conditional firing. If a token has a particular value, actor has to fire. If we have some kind of a requirement like that, SDF is not the choice. For this, we have the dynamic data flow actors, DDF, which can have multiple firing rules. They are not constrained to produce the same number of output tokens on each firing, and delay actor is directly supported by the dynamic data flow model of computation. There are two basic actors, select and switch. Let's look at the select actor. So basically, from the name, it's obvious that the select actor actually has three firing rules, and it has a firing rule at the it has an input port at the bottom, which is basically a Boolean input port. If the input port value is true, it takes input from the top input port, and if the value is false, it takes input from the second input port. Okay, so these are the two input ports which it selects its input value from. So basically, this is a selector kind of a port. So this is a select actor, and it's quite simple. So here, based on the value that you provide to this bottom port, it selects the one input port, the token available at the input port 1 or the input port 2. Now it fires twice to produce one input. So what does that mean? It means that it fires initially to take a value from this input port. So this is the first firing from the bottom input port. Now based on this value, it fires a second time to select an input from the input port 1 or input port 2, depending on the value that is provided at the bottom input port, to produce an output value at the output port. This is basically the select actor. Now looking at the switch actor, which is kind of like the complementary of the select actor. If you actually provide an input value at the left input port, and if you provide a Boolean value at the bottom output port, you actually get an output on the output port 1 or output port 2, depending on the value that you have provided at the input port and the bottom input port. So basically, again, this is a selector. Basically, this is a selector for the output. So this is a switch actor. Now let's move forward and take an example of a switch and a select actor. It's quite straightforward. Now it uses a select actor here. Basically, this is the this is the switch actor here, and that is the select actor here. It's a select actor here. So we have the switch and the select actors that we just explained. So here we can see that the input value that is received from A is it's basically switched depending on the value from B. It uses this value from B to decide where to route this value to. Basically, do we need to send it to C or D? And you can see that the number of tokens that are produced have been clearly mentioned here basically. So this is just like a synchronous data flow, or basically it's a balance equation between each set of actors. But the only thing that we have introduced here is the select and the switch actors, whose only functionality is to perform conditional firing. So here depending on the value from B, we actually select which port to forward to, basically reaching actor C or actor D. Similarly, the output from actor C and D are again selected based on the value from B, and it's sent to finally the output is sent to actor E. Can you guess what kind of a construct we have tried to implement here? Maybe you can just pause this video and try to find out like what is the construct that we have implemented here. So this is the hint that it's a construct, and the kind of selection that we are doing here is basically selecting a particular path of execution. So can you just guess what is the construct that we implemented here? So basically the construct, if you have guessed, it's an if else construct that we have implemented here. So moving forward, we can see that we can no longer find a bounded buffer schedule, nor can we provide assurances that the model will deadlock. So this is one important thing that we need to consider. We can no longer find a bounded schedule for this, because this is expressive in the sense that we can have conditional firing, but finding a bounded buffer schedule even in this kind of flexible using flexible actors like select and switch, we can either provide assurances that the model will not deadlock. So this is one thing. Of course, there has been a work by Buck in 1993 that shows that bounded buffers and deadlock are undecidable for DDF models. So in exchange for the increased expressiveness and flexibility, we have paid a price. The models are not as readily analyzed as a synchronous data flow model. So this is one shortcoming of the DDF. Okay, so we will just have a look at one of the examples in Ptolemy. This example will be used to explain the switch and the select actors. So we will be selecting this example, which is example 3.10 from Ptolemy. Okay, so let's have a look at this example. Okay, so here we actually have a Boolean switch and a Boolean select. Now this is a ramp function. Basically a ramp function, it actually produces a ramp kind of a wave. So its input is going towards a Boolean switch. So a Boolean switch basically is kind of the same Boolean select, the switch actor that we just described. Similarly, the Boolean select is the select actor that we just described. So the input to the Boolean switch is basically a Bernoulli actor. Basically produces a token or a value based using a Bernoulli distribution. So using the Bernoulli distribution, you get a value. Maybe the values for a Bernoulli distribution, as you know, it will be 1 or 0. So the complementary values that are input to the bottom port and the input from the ramp function, it will basically decide based on the Bernoulli output from the Bernoulli actor, and it will be scaled. Basically, if the value is 0, it will be -1. It will be decremented, else it will be incremented, and finally the output is again selected based on the Bernoulli input, and finally we get a sequence plotter. So let's try to run this and see what will be the output. Okay, so this is the output that we obtained. So initially the values are basically 0, and then the values keep on increasing. It keeps increasing in the negative as well as the positive direction. So if you try to run this again, you can see that the values have been the values are present on either side, because we have two scale actors. So we have one actor where the values move in the negative direction, negative part of the axis, and similarly along the y-axis. Similarly, the values move on the positive side of the y-axis when you scale it by +1. So the Bernoulli actor values, you can see, are basically used to select when this in which direction the produced values are actually incremented, either in the positive or the negative direction. So this is basically a ramp function. So this is the ramp that you can see here. So since the ramp function is always the ramp function is basically on the positive side, so if maybe you can just customize this and configure it. So in order to make it, maybe you can make it -2 and see what happens. So you see that in the negative side, the ramp is slightly on a more elevated side rather than the positive side, since I just modified that value of scale. So what if I don't scale this? So I'll just let me remove this scale and I make it 0. Similarly, if I just configure this and make it 0, I can just try it again. So you see that basically you have the ramp is it has just become a straight line on the x-axis. Okay, so there is no scaling that's happening. Okay, now if I just scale this as simply 1 on both sides, on 1, and try to run this again, I just get a plain ramp function. This is the plain ramp function that I get. So hope you got an idea about this Boolean switch. You can just take a look at this example. It's in page number 115 of the Ptolemy textbook. Okay. Yeah. Okay. Yeah. So this is what I just explained. Let's go to the next derivative, which is called a structured data flow. Now, if you look at this, we can see that the switch and the select are basically data flow analogs of go-to statement. Using them can result in the models that are very difficult to understand. Now, so switch and select are basically analogs of go-to statements. So, you know that if you have go-to statements in your program, they are basically difficult to understand, because the go-to statements actually create a kind of flow which it's very difficult to understand how the program flow goes. So, if you have written assembly code, you might probably remember the go-to statements or the C programming code that you have written. So, Dijkstra in 1968, basically Dijkstra indicted the go-to statement was not good. Basically, he discouraged its use and said it's not at all appropriate to use go-to statements in a good programming practice, and he advocated the use of structured programming. So, structured programming basically doesn't use go-to statements, use conditionals, and it uses loops like if, else, do, while, and recursion to basically produce structured programming. So, let's have a look at how the structured programming can be implemented in using the Dataflow model of computation. So, the concept is the same. Basically, we have a higher order actor which is called a conditional, and it has one or more models as parameters. So, this makes it more interesting. So, you see that there is a gray box that is bounded here, and the gray box is divided into two basically. So, they have two parts, and each part is basically a model. So, there is a model within this actor, and the models actually are conditional. So, if you, depending on the value at the bottom input port that you see here, we can decide which actor to fire. Should we fire this actor or should we fire this actor? So, basically the conditional actor decides which model to execute. Basically, should we execute the model containing C or the model containing D. So, the input value that is received from A will be sent to either model which is selected, and the value that is produced by the model is sent to E. So, this is a higher order actor which comes in the category of higher order actors in Ptolemy, and this is called a conditional actor. So, we will see this actor in detail. So, why this is called structured data flow? Because basically much like structured programming, rather than just using just redirecting the outputs, it uses control construct, and basically there is a hierarchical nesting. So, this is one hierarchical composition that we are using for this conditional actor. So, the model is still an SDF model, and the arbitrary data dependent token routing is avoided. Every actor consumes and produces exactly one token on one output, and the model is analyzable for deadlock and bounded buffers. So, this is one very important aspect. The model is analyzable for deadlock and bounded buffers. So, this is one advantage of using this thing. So, we have another example from Ptolemy, which we will see here, which is basically an example that I wanted to show you of a higher order actor. So, this is a higher order actor which is called a case. Now, let's try to get the documentation for this actor. So, this is a case actor, and this actor executes. So, you can just look at this. This actor executes one of several refinements depending on the value provided by the control port parameter. To use this, you have to drag the case icon. So, basically this actor is the example of the structured data flow that we just saw. So, let's just go back and see and just try to maximize this. Yeah. So, let's try to open this actor and see. I'm sorry. So, I will just open this actor and let's see what it contains. Okay. So, this is the default value that the actor executes. It takes a value as input and scales it and gives it as output. So, basically this is having a nested model inside. So, here again I am giving a ramp actor and the output is a sequence. So, the previous example that we just saw, I have just implemented this as in a structured data flow manner, and for this I use the higher order actors. You can find the higher order actors in the actors higher order. Okay, I guess that I have a small problem. So yeah, so anyway, you can just find this higher order actors inside this section, higher order actors, and you can find this case actor inside that. Yeah. Okay. So this is the case. So let me run this actor and see. Yeah. So we got the same value. Okay. So let's open this actor once again and see. Yeah. See how. So let me just modify this value, and I'm just okay. So there is yeah. So basically there are So basically there are two values here. Okay. So okay, yeah. So there are two values here. There is a true case and the default case. So in the true case, we have the scale value. Each time we increment the scale, we actually increment it by -1 in the negative direction, and here we actually scale it by 1 in the positive direction. So basically, we are not scaling it; we are just multiplying it by 1. So we are retaining the same value of the signal. The only thing is that we are just multiplying it by -1 in the negative direction, so that the ramp function is displayed in the negative direction. Similarly, we are multiplying it by +1. So we have two different models. So rather than having a select actor, we are implementing this using a case actor and considering two separate conditions. So this looks more elegant and more structured rather than the other previous actor. So here we have a separate model. So you can have any kind of model here, and you can just implement this into the case actor. Okay, there are other higher order actors also, which I won't be discussing here since it's out of the scope of our discussion. Maybe in the hands-on we will have more discussion regarding that. So this is a actor. We just get the same output from this actor as previously. So maybe we can just try modifying it finally and see what change that we can make here. So I am just going to customize this and make this 1, and I will just commit this. So what I will get here is, I will just see that I will just getting the plain ramp function as I got earlier. So in both the case, I am having this as one. This is 1 and this is 1. Okay. So that's all about that, and it's an alternative way to accomplish conditional firing. Okay. So moving forward, now we will move to the next kind of type of models of computation, other models of computation outside DataFlow, which is called a process network. So this is closely related to DataFlow model, and it's usually called a CAN process network because it was proposed by CAN initially. And in process network, each actor executes concurrently in its own process. So this is one important thing. There is a process involved, and each actor has their own process. Basically, it's a non-terminating program that reads input tokens, data tokens from the input ports, and writes data tokens to the output ports. It sounds very simple. Now, it can perform blocking reads on input ports whenever the process is to read input data. It means what does this blocking read mean? It means that the process chooses to access data through an input port, and it issues a read request and blocks until the data becomes available. So it chooses to access data through input port, it issues a read request and blocks until the data becomes available. It cannot test the input port for the availability of data and the perform a conditional branch. It cannot test the input port for the availability of data and then perform a conditional branch on whether the data are available. Okay, because such a branch would introduce schedule dependent behavior. So this is not possible in this process network. So blocking reads are similar to firing rules. Okay, so blocking reads, if you compare the blocking rules, they are similar to the firing rules, because in the firing rules we only fire when we have certain tokens that are available. Okay. Okay. Now moving forward, we can also have a non-blocking write, where the process does not block to wait for the receiving process to be ready to receive data. So this is exactly how writes to output ports work in DataFlow models of computation as well. So the process network model of computation poses challenging questions about boundedness of buffers and deadlock. It's expressive enough so that these questions are undecidable. So again, Just like we have the dynamic data flow, the questions are undecidable, and the process network is expressive enough, but the questions are undecidable. So that's the price that we have to pay for that. Okay. Now, if you compare the data flow and the process network, the actor is not broken down into firing functions. They are designed as a continuously executing program, and in a process we have each component as a process network coroutine. Okay, we usually call that a coroutine, which the processes in a process network are called a coroutine. Now there is a variant of process network which is called a rendezvous, and a rendezvous performs blocking rights. Its basis is well known process formalisms like communicating sequential processes. We have calculus of communicating systems. So you must have heard of both of this, CSP as well as CCS. CSP is from Hoare and CCS from Milner. Robert Milner forms the foundation for the so CCS forms the foundation for the Occam programming language. Now let's quickly just touch upon the role of time. So this is important here because we need to understand what concept of time does this the model of computation actually impose or provide. Synchronous reactive systems and Dataflow models computations, they in both these systems time plays a minor role. So in Dataflow there is no role for a time. Basically time doesn't play any role. The only thing that happens is when you have tokens available, you start firing and produce tokens on the output port. In a synchronous reactive system, you might think that time plays a role, but in fact the exact notion of time, it doesn't matter, because the computation occurs simultaneously and instantaneously at the tick of a global clock, but it isn't about the time, it's just about the clock. So when a clock works, it performs some action. It doesn't matter when the clock has to work or how the tick of the clock has to occur. The physical time at which the ticks occur, it's irrelevant to the model of computation, just like the sequence of ticks, it doesn't matter. So let's look at other model of computation that has explicit notion of time. So we are going to talk about some timed model of computations like time triggered models and discrete event systems, and we are going to focus more on the discrete event systems. So for cyber physical systems, the time at which things occur, it doesn't it matters, okay, because these software actually interact with physical process. So there is an architecture which is called a time triggered architecture, and the mechanisms of periodically triggering distributed computations according to distributed clock. So what do you mean by a distributed clock? A distributed clock is something that basically means that everybody has a copy of the clock, basically have a copy of the time, and they share their values with a synchronizing agent which synchronizes the clock across all the other nodes or the actors basically. So it measures the passage of time, and the TTA could tolerate certain kind of faults. The failures in part of the system could disrupt the behaviors, and so this is one advantage of TTA. The failures in one part of the system could not disrupt the behaviors in other part of the system. So I'm not going to detail about how this is implemented, but probably you can try to guess some aspects of TTA that could enable this feature here. Now techniques are coming to practical use with the design of safety critical avionics and automotive systems. So flex array kind of protocols that have been used in automobiles are basically taking advantage of this kind of aspect that is enabled through the use of time triggered architecture. Now a time triggered architecture is similar to a synchronous reactive system, okay, because there is a global clock that coordinates the computation. But in a synchronous reactive system, we know that the execution is basically instantaneous. But in the case of a time triggered system, this is not instantaneous, it takes time. So when I mean it takes time, I mean to say that it takes a finite time for execution. So rather than being instantaneous, it takes time, and it instead of being simultaneous, and so there is no concept of being simultaneous. So in a synchronous reactive system, being simultaneous is just a notion. We cannot really say that it's simultaneous and instantaneous, but for the purpose of the semantics, we consider that it's both simultaneous and instantaneous at the same time. But time triggered MOCs, they associate the computation with a logical execution time, and inputs to the computation are provided at the ticks of the global clock. The outputs are not visible to other computations at the next tick of the global clock. Between ticks, there is no interaction between the computations, and concurrency difficulties such as race conditions do not exist, because we are not going to perform any kind of interaction between the computation. So what is the verdict? Time-triggered models are conceptually simple. The computation are tied closely to a periodic clock, and model becomes awkward when the actions are not periodic. So when the actions are not periodic, the model becomes awkward. Why? Because it's a totally asynchronous model, and if we have a lot of actions that are not periodic, the model becomes quite awkward. Okay. So now we will move into the discrete event systems. So let's start with discrete event systems. Discrete event systems basically they are model of computation where there is an exact and precise notion of time. So the core aspect of a discrete event system is we have several concurrent actors and we have discrete interactions between these concurrent actors. So when we mean discrete interactions, we know that there is each interaction can be specified as an event. So if you take an example of a discrete event system for an Internet of Things application, for example, an IoT application, we have several events that occur in a real time or maybe non-real time. The events that occur are basically the events that happen from the physical environment, and these events are basically occurring in a specific with a specific notion of time, in the sense that the events occur at certain periods of time, and we can actually put these events in a queue according to the timestamp of their occurrence. For example, we may see that particular temperature may be rising in a certain part of a building, and we then later determine that the output of a smoke sensor or a fire sensor is it also produces certain events or certain data, and these are basically ordered in time. So this is the most important aspect of a discrete event system, when these events are ordered in time, because if we have events that are not ordered in time, or if you take the example that the temperature remains the same and there is smoke, so that may sound strange, or it may be not exactly due to the occurrence of a fire. It may or may not be. So we are not precise. So the time at which the events are generated are very important in a discrete event system. And basically in a discrete event system, we have an instantaneous message that is sent from one actor to another. Now, event in Ptolemy 2 is a token which is basically encapsulating a message. It's arriving at a particular model time. Okay, it arrives at a port at a particular model time. So what is this model time is one question that we want to look at. We will have a look at that as we move forward. Now, what is the key idea? Basically, that is what I just explained. Each actor reacts to input events in temporal order. We have a specific ordering of the events according to their timestamp. So the model of time is essential to the operation of discrete event systems. If you look at discrete event systems, they have been used for decades as a way to build simulations. Digital networks, military systems, and economic systems. We had a formalism of discrete event system specification by Ziegler in 1976, which was a pioneering formalism in this particular area. He proposed the discrete event systems as extension of Moore machines, and with each state he associated a non-zero lifespan. Okay. Now, events are endowed with a key timestamp and a value in some model of time. So, as I already specified, for example, a sensor producing data may be the data of the sensor may be sent across, it may be transmitted to other nodes with a timestamp saying that this was the recording of, this was the value of the temperature sensor produced at this particular point of time. Most important aspect is we can't have a same instantaneous event, in the sense that two events may not have the same timestamp. Okay, so if events must have different timestamps, in any case, due to clock drift or due to any other reasons, if two events have the same timestamp, we look at the micro step to be precise whether it is a strict ordering. Okay, so we will talk about that. Now, in a network DE model, there are a network of actors. Each actor reacts to input events in timestamp order, and most importantly, they produce output events also in timestamp order. Of course, this may sound obvious, but the important thing is the output produced in timestamp order also matters in discrete event models. In order to understand the precise notion of time, let's have a look at what exactly is a clock. So if we have a clock, we have already seen this earlier. A pure signal, the S, that is a discrete signal, can be represented, can be specified that S of t is present if t is a multiple of a value p, okay, and t belongs to the real domain, and it is absent otherwise. So we have a discrete signal that is present if t is a multiple of p and it's absent otherwise. So we have p, which is a period. So we have t at each point, each period, or maybe probably each period of time, we have a signal that is present. So here we associate, or we define a pure signal that is a discrete signal at specific intervals of time. Now we can call a signal, such a signal, as a clock signal, and it will have a period p, and it occurs, the communication events occur at every p time units. Now if you look at example 6.16 in the textbook, the clock signal with period p of example 6.1 consists of events with timestamps np for all n belonging to the set of integers. So here we see that we have a clock signal, okay, and it's of period p, and of this that we just defined here. It consists of events with timestamps np. Okay, so here n belongs to the integer domain, so we have whole numbers rather than real numbers. So the period p is the basis for the timestamps np, which stands for n is the np, which is period p, which stands for at each period we have, or so p can be 1 second, p can be 1 minute. So there is a specific period for which the clock signal is defined. So this is the discrete definition for the clock signal. Now we can have different methods of execution, but for a discrete event model we use an event queue, which is quite straightforward. It has a list of events that's sorted by timestamp. The list initially, of course, is empty. Each actor in the network is interrogated for initial events that it wishes to place on the event queue. So the events may be for the actor itself, or it may be for other actors. All these events are basically stored in the event queue. Now we have to execute this particular queue by selecting the earliest event in the event queue and determining which actor should receive that event. So this may sound straightforward, but in conditions where we have real-time systems, we need to associate priorities for these events. We will see that in brief as we move forward in this lecture. So in the straightforward case, if we have several events that we wish to place on an event queue, we select the earliest event according to the timestamp and we determine which actor should receive that event. So this is what a DE actor would be doing. So just like we had a SDF actor, we also have a discrete event actor. So value of that event, if any, is presented as an input to the actor, and the actor reacts or fires. Now, the reaction can produce output events and the events that simply request a later firing of the same actor at a specified timestamp. So the response may be instantaneous or it may be deferred. Now let's look at an example from Ptolemy, where we have an example of a discrete event application. Now this application is this example is quite motivating due to several reasons. So I will just open the example in Ptolemy. So this is the example. Now if you look at this, this example basically this example of a discrete event system is quite motivating due to reasons that we will see. So this is a diagram of the model, and we have 4 actors here. Of course, this is a modal model. We will see this modal model in detail. This is a common application of a discrete event system, where we are actually modeling the faults or error conditions occurring at random time. So there can be a situation where a model is usually stuck at fault. When it's stuck at fault at a particular random time, a signal becomes stuck at a fixed value and no longer varies with input. So you might have seen this kind of problems in common electrical or electronic appliances, where we usually get stuck at fault. So a particular fault occurs at a certain random time and the system gets stuck at this particular point, and the signal value is stuck and it no longer varies with the input. For example, if you have an MP3 player or an audio player, you might notice that at certain points of time the audio player gets stuck, and the music that's emanating from the player, it's stuck at a particular point, and all you hear is the a noise or a certain sound that keeps repeating or just howling. So this is kind of example where you can see that signal becomes stuck at fault. Now we will use this example to illustrate why it is important that events be processed in timestamp order. So let's go back to the example and see how it's actually working. So we have a discrete clock, we have a Poisson clock. So we have a discrete clock. Basically this is a discrete clock which drives this model, and we have the Poisson clock, which basically produces random events in order to generate the fault. So let's open this actor to see what's inside the modal model. So inside the modal model we have 2 states for a finite state machine. So these states basically are normal and error. So what happens is when we have the clock signal is basically drives the system in the normal state, and in case you receive an error signal at a random point of time using the Poisson clock, which is basically generating sequences from using the Poisson distribution, it generates certain error signals at certain periods of time, and at that point the state machine moves towards the error state, and in the error state it remains throughout. It doesn't transition back to any other state. So this becomes the final state, and it keeps in this state. The output status will be 0. So when it's in the normal state, the output status is 1, and when it's in the error state, the output status is 0.
So this is what's inside the modal model. So basically the two inputs, the discrete clock and the Poisson clock. Discrete clock drives the discrete event system. The Poisson clock drives the it generates certain error signals, okay, at certain periods of time as defined by the Poisson distribution. We have the DE director here which drives the system, and we have a time to plotter. So let's see how this works. Okay, so yeah, so you can see that we have signals initially, and then error occurs, and then the signal becomes stuck. So this can happen anyway because the Poisson distribution basically generates random events. So we see that at certain point of time, for example here at 5 and 6 we have an error, and then the system becomes stuck at fault. Now the question is why we want to model this as a discrete event system. So it's quite simple. If we actually have the clock signals we receive, the model receives both the values, the clock signal and the error signal from the actors, and it puts it into a time queue based on the timestamp. So depending on the timestamp which the DE director handles, the timestamp basically is used to put the events into queue. So we have the normal clock events that occur, and then we have the error event that occurs. So in case we have an error event is occurring, if we had a separate director, instead of a DE director we had a SDF director or we had an SR director, we couldn't say exactly when this error signal would happen because the processing is not dependent on the notion of time. In a discrete event system, then the notion of time is clear, and if the error signal has occurred after the discrete clock has fired, definitely it will be put at the end of the queue, and the processing will only take place on the timestamp order. So otherwise, in any other case, in a case of a data flow or in a case of a synchronous system where notion of time is not present, we cannot guarantee that the error will occur at the exact time. It may happen earlier, or the error signal may be produced and the error may happen earlier, or system may always be stuck at fault. So this is one reason, a simple motivating example of handling faults and why discrete event systems actually are useful in this situation. Okay, so let's go back to the presentation. So if you look at a discrete event system, an actor connection carries signals that consist of events placed on a timeline. So here we see that we are talking about events which are placed on timeline. Each event has a value and a timestamp. We have already mentioned this before. A timestamp defines global ordering between events. So what is the case of a data flow system? A signal consists of basically a sequence of tokens. So this is what we started our discussion with. There is no time significance in the signal. Now, timestamp is a super dense time value consisting of a model time and a microstep. So we have a real world time, we have a model time. A real world time is the real world time, the actual time that we actually see, and the model time is a time that is the clock reference in the case in the model during model execution, for example in Ptolemy. And a microstep will be like something similar to a nanosecond or a microsecond, and it will be basically a super dense time value. So because we might have in particular second, for example in a particular model time, during a second we may have several events, so we need to determine which event occurred first. So we need to look at the microstep. So the timestamp is basically a super dense time value. So the precision in the case of simulation is not of significance here. The more important aspect is that time is represented as a model time and a microstep. Now a question that arises is how simultaneous events are handled. So this is an interesting question. This I previously I had described to you in a couple of slides earlier that I will be talking about this. Now we have this strongly simultaneous events and weakly simultaneous events. So strongly simultaneous events that I just told you have the same timestamp. They have the same model time and the microsteps, which is means that they are really simultaneous. But weakly simultaneous events have same model time but not necessarily the same microsteps. So they may occur at the same second, maybe not at the same microsecond. So the events are processed in chronological order, but if two events have the same timestamp, which one should be processed first is an interesting question. Whereas if we have the same timestamp, same model time, same microstep, which one should be processed first? So we just open this example from Ptolemy, which is example 7.3. So this is an example where we have two events that occur, and this is there is an event. So we have a Poisson clock, which triggers a current time. So at random periods of time, we have values that come from this current time, and we have an actor which is called previous. Okay, and this actor basically just try to understand what this actor does. Yeah. So this is what the actor does. It produces the token received in the previous iteration. In the first iteration, it produces the token given by the initial value, if such a value has been set. Although it might be tempting to try, this actor is not very useful for breaking precedence in a feedback loop in DE, the way the time delay actor in DE or sample delay actor in SDF2. So we have a time delay actor in DE, just like we had a sample delay actor in SDF. Now, so this is since it does not trigger until there is an input, it will not actually break the precedence in a feedback loop. So let's have a look at this actor and how it is configured. So we have an initial value that is set. The initial value will be the value that it produces on the first firing, and the next firing it will just copy the values from the previous iteration. So now we have two inputs here for this add subtract actor. So basically adds and subtracts values from they received on the two input ports. This is basically a polymorphic adder subtractor. It has two input ports. Okay, so that's straightforward. Then we have an histogram plotter. So if you look at this, we have a Poisson clock, which basically triggers a current time and which is given as input in both the loops. So here we have a handling of simultaneous events, which is basically the input to the add subtract polymorphic actor. So let's try to run this model here and see how it looks. So this is basically how it looks like, and this is the histogram of inter-arrival times. So what is meant by inter-arrival times? So usually if we have several packets that are arriving at a particular port, for this is an example, if you have several packets that arrive at a particular port, if you take the time between the arrival of the packets, this is referred to as an inter-arrival time. So if you look at the inter-arrival time, we can see that the inter-arrival time between the packets, basically it can be triggered by a Poisson clock. So a Poisson clock, basically usually we model this, or we approximate the inter-arrival times using a Poisson distribution. So that is one reason why this Poisson clock is being used here. Now the Poisson clock drives the current time, which gives as input the current time to the add subtract and as well as the previous. So basically we are just plotting histogram. So we see that in the histogram we can see that so one interesting thing about the previous actor is that one interesting aspect is that it produces the same timestamp. So the timestamp at which it receives the input value and the output value it produces at a certain timestamp. Both are basically same. So here what happens is the timestamp that we receive at the add subtract actor plus port, and the timestamp of the event that we receive at the so the timestamp that of the event that we receive at the minus port are basically the same. So this actor has been deliberately added here in order to raise two events which have the same timestamp. Now we want to see how the DE director handles this. So we have two strongly simultaneous events, one at the input of the plus port and other at the input of the previous actor. So the question is, should the director fire the add subtract actor or the previous director first? So we have two events that have the same timestamp being sent to the both the actors. Should this actor be fired first or should this actor be fired first is one question. So we can have you can say that both are basically fine, but we want that the previous actor should be fired first so that the input that are available are valid, and in this case the DE director will of course fire this actor, previous actor first, and then it will fire the add subtract actor. Okay, so it will be as the previous actor will be fired first and the add subtract actor will be fired second. Now I'm not just telling this, but we will see this how it happens. So the order of firing is basically governed by something which is called a topological sort of the actors in the model, which is basically a list of actors in data precedence order. So we are talking about data precedence in this case. So the DE director also takes into consideration data dependencies, although this is not like the data dependency in a DataFlow model. So here we have a topological sort that is performed based on the data precedence, and if there are multiple valid topological sorts, so there may be multiple, this is a simple model, but there may be a complex model, we have multiple valid topological sort that is performed, but all that so in that case we say that the events are always in timestamp order. So it the analyzing the structure, the DE director analyzes the structure of this model and it delivers determinate behavior. So the actors that produce data are fired first before the actors that consumes the results, even in the presence of simultaneous events. So I hope that is clear. So all the actors that produce the data are fired first before the actors that consume the data, even in the presence of simultaneous events. So this is the only case when we have simultaneous events. Suppose the timestamp of the event that was received here was later, then this would not arise, because we are talking about either non-simultaneous events or weakly simultaneous events. The context of this discussion is only based on strongly simultaneous events. Okay. So this is basically the topological sort that would happen here. Now the topological sort that would usually that would be the sorting that would happen here is basically the Poisson clock will be first, then the current time, the previous actor, the add subtract actor, and the histogram. So this will be the Poisson clock will be put in the in the list first, then we have the current time, then we have the previous actor, the add subtract actor, and the histogram plotter. So this is basically how discrete event handles strongly simultaneous events. Okay. So let's move back to the presentation. Now this example 7.3 has a problem. So is it possible for you to identify the problem? Let's see if we can identify the problem.
So let's see whether we can identify the problem. Okay. If you want to identify the problem, you have to start looking from here. I hope you guessed it. Probably it's correct. The problem that we can see here is in the initial firing. In the initial firing, we see that the timestamp of the first event produced by the Poisson clock is basically 0. At this moment of time, the output produced by the previous actor will be null. It will not be producing any output. So the first output of the add subtract actor will have a value of 0, which is not in fact an inter arrival time. Thus the plotted histogram includes a spurious value which is called 0. So how do we so you must have noticed that here in this place you can see there is a value, spurious value 0, that happens due to this problem. So how we can fix this? We can have a different solution for this. So let's try to see that solution here. So this is the solution to the problem that we just saw. Here we actually have extra actors. So we have a sampler actor which we have added as input to the plus port of the add subtract actor. Now the previous actor will be connecting to the sampler actor and the current time also will be going to the sampler actor. We will have be taking the output from the sampler actor to the add subtract actor, polymorphic actor. So this is how it the solution to this problem can be we can fix this problem. I would suggest that you go through this example and it will give you a clear idea about how the clock signals work. Okay, so let's go back to the presentation. Now let's talk about scheduling. So how does scheduling work? Basically the main task of a DNet director is to fire actors in timestamp order. The D director maintains an event queue that is sorted by timestamp. So basically the task of a D director is to fire actors in timestamp order, and the D director maintains an event queue that is sorted by timestamp. It first the model it fires by model time and then by microstep time. So it fires by model time if all if the two events have the same model time, then the director will look at their microstep, and if the microstep, the event with the microstep which has an earlier microstep will be fired first. The D director controls the execution order by selecting the earliest event in the event queue and making its timestamp the current model time. So it then determines the actor the event is destined for and finds all other events in the event queue with the same timestamp that are destined for the same actor. It sends those events to the actor's input ports and then fires the actor. If after firing the actor it has not consumed all these events, then the director will fire again until all input events have been consumed. So the director has the job of firing the actors just like it did for the Dataflow model of computation and synchronous reactive model of computation. The actors are basically fired until they have consumed all the input events. Here we use an event queue in the case of a discrete event system. Now how do we ensure determinism?
the DE director uses a specific rule to ensure determinism. What is this specific rule? It has guarantees that all events that have timestamp equal to the current stamp before it fires the actor. So this is one important thing. All events having timestamp equal to current timestamp before it fires an actor. Okay, it guarantees, it has provided all the events the timestamp equal to the current timestamp before it fires the actor. So this is what I just mentioned in the previous slide. So once it has guaranteed that it has provided the events having timestamp equal to the current timestamp before it fires the actor, it cannot subsequently provide an additional event with the same timestamp. So the additional event cannot occur with the same timestamp. It may have the same model time, but it won't have the same microstep. So this is how the determinism is ensured. So we must make sure that we get an idea of how the DE director ensures determinism, or as a matter of fact, how the DDF factor or the SDF factor also ensures determinism. Now, how DE model of computation behave differently? So the discrete event system specification requires that the outputs produced by the actor has strictly larger timestamp than of the input just presented. That is one requirement. So that we make sure that there is a difference between the timestamps, so that the events can be processed in chronological order. Now, in every actor imposes a known zero delay. This is one important thing. So the outputs become visible to the other actors strictly later than the inputs that triggered the reaction. So there is some delay, and this is very important in the case of a discrete event system. And other variants of the discrete event system permit the actor to produce output events with the same timestamp. So I just showed you this actor, which was the actor that we just saw, which is the previous actor, which had a capability of producing the same timestamp event. It produces an event with the same timestamp of the event that it had received at its input port. Now, we can also have a DE as a generalization of the synchronous reactive system. So if we have an event queue, and if we interrogate all the actors for initial events to place on the queue, select the events from the queue with the least timestamp and all other events with the same timestamp, present those events to actors in the model as inputs, fire all actors in the manner of constructive fixed point iteration as normal with SR. So in this variant of the semantics, any outputs that are produced by the actors must be simultaneous with the inputs. They have the same timestamp. So they participate in the fixed point. This is what the synchronous reactive systems that we have seen. So once they are in this fixed point, they participate in the fixed point. We must ensure that they participate in the fixed point, and the outputs should be simultaneous with the inputs, as with a synchronous reactive system. If an actor wishes to produce an output event at a later time, it does so by requesting a firing at a later time, which results in the posting of an event on the event queue. Okay, so let's now wind up this discussion and this lecture. Synchronous reactive models are closest to the synchronous composition of state machines. Dataflow models where execution can be more loosely coordinated, only data precedences impose constraints on the order of actor computations. The models of computation that explicitly include a notion of time are basically time triggered models, for example discrete event systems. Such models of computation are particularly useful for modeling cyber physical systems. So the entire discussion on models of computation is to ensure that while designing different kinds of systems, we need to make sure what will be the semantics of the interaction between the various components. Even in the case of the hands-on that you are currently doing, I have proposed that since most of the applications are basically can be modeled as discrete event systems, it would be really interesting if you could just have a look at the other models of computation like synchronous reactive and Dataflow model of computation and see how your application can be modeled with such a model of computation. What are the shortcomings? So it doesn't there is no harm in looking at what way your system will behave if it were a different model of computation. So please have a look, and you can definitely try it out in Ptolemy, since Ptolemy has a lot of different directors that you can experiment with. So thank you for listening to this lecture, and I hope that you will be looking at the examples I have provided. The reference to this discussion is basically the textbook chapter 7, chapter 6, which is the chapter in the Professor Edward Lee's book on embedded systems. And the discussion on Ptolemy, the chapters are basically for chapter 3 for data flow and chapter 7 for discrete event models. So once again, thank you for listening.